Okay, AP Statistics students, so we're moving on to section 10.2, which is learning to compare two means, or what we call the two-sample t-test. In section 10.1, we learned about the two-proportion z-test. Now in section 10.2, we're going to be learning the completely similar two-sample t-test. If you have a level of comfort with the two-proportion z-test, this should not be too bad. So, when we say that we're going to compare two means, we could find ourselves in one of two different situations. We could be comparing two population means, mu1 and mu2, and if that's what we're doing, we'll draw random samples from both populations and we'll get x bar 1 and x bar 2. And we'll compare the sample means in order to infer about the population means. Or, situation number 2, we could be comparing the means of two treatment groups. We will still compare the sample means of the treatment groups in order to infer about how the population may react to the treatments. So, just like any other significance tests, to run a two-sample t-test, state, plan, do, and conclude. So the first part of a two-sample t-test is we will state both of our parameters. Let mu1 equal the average of population 1. Let mu2 equal the average of population 2. And of course we'll use context when we're doing that. And then our null hypothesis will always be mu1 minus mu2 equals 0. And our alternative hypothesis will either be mu1 minus mu2 is greater than 0, or mu1 minus mu2 is less than 0, or mu1 minus mu2 is not equal to 0. You should be used to that by now. Then, for the plan phase, we check the conditions for the two-sample t-test. Well, you guessed it, the conditions for the two-sample t-test are exactly the same as the conditions for the one-sample t-test from Chapter 9. You just have to check the conditions for both populations, both samples, excuse me. Were both samples random? Or were subjects randomly placed into treatment groups? Are both samples less than 10% of their respective populations? If so, that means the two samples are independent. If both samples came from normal populations, great. Just state that. But, as we've seen, if the sample sizes are both greater than or equal to 30, that satisfies the conditions for a two-sample t-test. But if the sample sizes are smaller than 30, if you have raw data, graph the data and check for symmetry. Again, this should sound completely familiar to you. So, now all we have left is the do and conclude. And as I say right here, you already know how to draw conclusions based on how the p-value compares to the alpha level. So we don't need to go through that until we just do some examples. Now, for the do phase, we need our formulas. And these formulas should kind of feel familiar based on how I developed formulas for the two-proportion z-test in the previous section. The first thing you have to do is make sure that you know x1 bar and x2 bar. And then once you know your two sample means, you're going to subtract those two sample means because we have to get our observed difference between the two means. We're comparing the two means. We subtract them to get to see how different they are. Okay, now, over here on the right side of the slide, similar to what I did in section 10.1. In Chapter 9, we learned that the standard deviation of x bar was sigma over the square root of n, where sigma is the population standard deviation. Well, the weird thing about that formula is the population standard deviation is rarely known. So you can't divide that by the square root of n to get the standard deviation of x bar. But what we did learn is that we can instead calculate the standard error of x bar as s over the square root of n, and that would be the sample standard deviation divided by the square root of the sample size. Now, the standard deviation of x minus y from chapter 6 was equal to the square root of the variance of x plus the variance of y. Well, we can't find the standard deviation of x bar minus x bar, but what we can do is we can substitute the standard error of x bar into the chapter 6 formula, and we can calculate the standard error of x1 bar minus x2 bar to be equal to the square root of the variance of x1 bar. Well, the variance of x1 bar will be the variance of sample 1 divided by n1 plus the variance of sample 2 divided by n2. So just imagine what I just did there was I squared this above, and that gave me s squared over n. So the variance of x1 bar is s squared over n, and the variance of x2 bar is s squared over n. So you put it together. Okay, and then of course, since we're doing a t-test, you still want to report your degrees of freedom. Now, I have to tell you that the degrees of freedom is not n minus 1 here. Let the calculator tell you the degrees of freedom. It's much too complicated to worry about. And of course, calculate your t-score and draw your picture. And in our picture here, just like the two proportion z-test, we're expecting the difference to be 0, but then we take this observed difference and we mark it, and we get our shaded area, and we calculate that p-value. So let's work through one example together to end this video, and then in the next video we'll work through a second example. Resting pulse rates for a random sample of 26 smokers and had a mean of 80 beats per minute and a standard deviation of 5 beats per minute. Among 32 randomly chosen non-smokers, the mean and standard deviation were 74 and 6 beats per minute. Both sets of data were roughly symmetric, oh that's nice, they just told us, and had no outliers. Is there evidence of a difference in the mean pulse rate between smokers and non-smokers? And how big is that difference? All right, let's get started. So I would say something like this. Let mu subscript s equal the average resting pulse for smokers, and let mu subscript ns equal the average resting pulse for non-smokers. So I've defined both my parameters. Now I'm going to say that the null hypothesis is mu smoker minus mu non-smoker is equal to 0. In other words, their resting pulse rates are the same, no difference. The alternative hypothesis is going to be mu s minus mu ns. Well, let's see. Is there evidence of a difference? So I guess I'm going to go for that not equal to case. If it had said, is there evidence that the mean pulse rate for smokers is higher, then I would have put greater than 0 there. Okay? All right, now we're ready to check the conditions. So I'm going to say all smokers and non-smokers were randomly chosen. So that's good. Okay. Okay, what else do we want to say? 26 smokers, less than 10% of smokers, and 32 non-smokers, less than 10% of non-smokers. Okay. Now, we would have a problem with this 26 smokers being less than 30. But you see right here where it says both sets of data were roughly symmetric and had no outliers, then the sample size doesn't really matter as much. So we can say something like, since both samples were roughly symmetric, a two-sample t-test is okay. Again, most of the time we want to compare our sample sizes. Are they greater than or equal to 30? Well, 32 non-smokers hits that, but 26 smokers was less than or equal to 30. That could have been problematic had they not clearly stated that both sets of data were symmetric with no outliers. So now we can run the test. So we have X bar for the smokers is 80 beats per minute. And we have that X bar for the non-smokers was 74 beats per minute. So if I take X bar smoker minus X bar non-smoker, that's 80 minus 74 equals 6 beats per minute. So you got to get that observed difference. Okay. Now you want to calculate the standard error of X bar smoker minus X bar non-smoker. And that equals the square root of, well, let's see, 5 beats per minute was the smoker standard deviation. So I want to take 5 squared over 26 smokers. That's a 5, not an S. Plus, the standard deviation for the non-smokers was 6. So I want to take plus 6 squared over the sample size of 32. So if I grab my calculator, I want to play the game and calculate that. So let's see, that's going to be 25 divided by 26 plus 36 divided by 32. And then we want to take the square root of that. I just got 1.79-ish beats per minute is the standard error. Okay, now I'm going to let the calculator tell me what t is equal to, and I'm definitely going to let it tell me what the degrees of freedom is equal to. But just remember, t is able to be calculated as the observed difference of 6 minus the expected null hypothesis of 0 divided by 1.79. So 6 divided by 1.79 is 3.35. So now, let's press menu and go down to statistics and go down to statistics tests, and you should be able to find the two-sample t-test. Looks like option number 4. Okay, you want to tell the calculator that you have statistics to put in, and then it asks for X1 bar. Well, for us, that's the smokers, and so that was 80. And then what is the standard deviation? Well, for the smokers, the standard deviation was 5. Okay, and then it asks for N1, the sample size, that was 26 smokers. Now it asks for X bar 2, which is the non-smokers, 74. Standard deviation for the non-smokers was 6, and the sample size for the non-smokers was 32. And then you make your alternative hypothesis the not equal to case. Press OK. All right, the calculator just told me that the degrees of freedom is 55.95. It's weird, just write it down. Okay, and by the way, I will also tell you that the calculator just told me that t is 4.15. Why is mine 3.35 and the calculator's 4.15? It's just a difference in rounding that 1.79 beats per minute. So don't worry about the fact that it's slightly different, okay? All right, so now draw yourself a t-distribution, label the center 0, and label the difference 6, but since the alternative is the not equal to case, go out to -6 and shade both wings. P-value is 0.0001, incredibly small. So what are we going to do? We are going to reject the null hypothesis. Hopefully you're writing more. Since the p-value is smaller than the significance level of 0.05, I reject the null hypothesis. So does that mean that there's evidence that there is a difference in the resting pulse rates of smokers and non-smokers? Now, by the way, you can also calculate a 95% confidence interval by taking the observed difference plus or minus the t-score times the standard error of 1.79. Well, you'd have to go look up the t-score in the table with that 55.95 degrees of freedom. But all you got to do is press menu on your calculator, go to statistics, down to confidence intervals, and find the 2 sample t interval. And the nice thing about it is you just enter very much the same data. I wish it just transferred over. So let's see what the confidence interval is. 80 is x1 bar. This is a pain. 5 is the standard deviation, sample size 26. x2 bar was 74 with a standard deviation of 6 and a sample size of 32. And then it says confidence level, set it at 0.95, and press OK. And let's see, it tells me, the calculator is telling me that the confidence interval goes from 3.1 beats per minute to 8.9 beats per minute. I am 95% confident that the average difference in the resting pulse rates is between 3.1 to 8.9 beats per minute higher for the smokers. Because the whole thing is positive, that tells me that smokers minus non-smokers is always above 0. All right, we'll end this video here and do another worked out example on the next video.